moving on to leaving group ability in a SN2 type reaction. Basically, the trends for leaving groups, the most important one by far is bigger is better. Again, iodide is bigger than bromine, which is bigger than chlorine. Iodide is a better leaving group than bromine, than is chlorine. This explanation, once again, is really about polarizability frequently. And the explanation here tends to be that you can smear the charge out over a larger area. That, in fact, fluorine is a terrible leaving group. And the reason why fluorine is a terrible leaving group is because it is a point charge. Though it's extremely electronegative, it doesn't really tolerate having charge very well because it's such a small atom and all that charge is concentrated in a small place. Whereas iodide, bromine, and chlorine are dramatically larger, they can spread out that minus over a larger area, and that lowers the energy. So I, being the biggest, is by far the best leaving group. And in fact, a good way of keeping track of this is the pKa short list. So minus 10 or so is the pKa for Hi, and then bromine also is excellent at minus 9, and then chlorine is excellent at minus 7. And fluorine is a bad leaving group because it's actually a fairly weak acid. If you're a strong acid, if you're the conjugate ion of a strong acid, you can really well tolerate having a minus charge ion. So these guys are conjugate ions of strong acids. They don't mind existing as minuses. However, fluorine is the conjugate ion of a weak acid. It does not want to exist as F minus. The difference between chlorine at minus 7 and fluorine is 10 to the 10th, 10 orders of magnitude. Another thing to keep in mind when you're thinking about leaving group trends is that the charge is bad. You don't want the leaving group to leave as a charged species if you can help it. So if you have this sort of group where an oxygen is existing as a plus charge right now, bound to some carbon, when it leaves as water. And it's an okay leaving group. It's not great, but it's okay. The pKa of the situation, the pKa of the protonated oxygen, is about minus 2, which is to say it's 100,000 times worse than chlorine as a leaving group. But it's not bad. pKa is about minus 2. That's really about the definition of what becomes possible. So water leaving, so leaving as water itself, neutral water, with a pKa of around minus 2, that's acceptable. The pKa of minus 2 refers to this species right here. This is the item with the pKa of minus 2. If you have a pKa of about minus 2, then the group can probably leave. However, in this case, what is the pKa of an alcohol? pKa of an alcohol is about 16, which is to say this is 18 orders of magnitude worse. This essentially does not happen. The OH minus does not leave as OH minus. This alcohol bond cannot break and have this leave at OH minus because it's just simply too basic. What you want is a conjugate base of a strong acid as a leaving group. Here, you actually have a base leaving. This is a base, a fairly strong base, so it doesn't want to leave. Again, the trends so far are bigger is better, but secondarily, it's better to leave as a neutral thing than it is to leave as a minus thing. One thing that's interesting is that there are several atoms that can serve both as leaving groups and as nucleophiles, and those are really the halogens. But other than that, the trends for nucleophiles and leaving groups aren't altogether that similar, because what makes something a good nucleophile, too much electron density, tends to make it a worse leaving group. Broadly speaking, your leaving groups really exist along this line, the halogen. And to the extent that that's not true, we actually have several additional leaving groups that you'll need to be somewhat familiar with. Other good leaving groups that exist, it's probably a little bit premature to talk about them and to start to use them, but it really fits in with what I'm trying to talk about here with the pKa's. So they are triflate, mesylate, and tosylate. When we start dealing with synthesis reactions of alcohols, you'll learn that this is a good way to take a hydroxyl group, an alcohol group, and convert it into a better leaving group. And all of these are roughly as good as, say, chloride to iodide, somewhere in there. They're in between, depending on the exact details of the situation. So a triflate is a trifluoromethane sulfonate. OTF is the abbreviation. Trifluoromethane sulfonate is the actual term, and this squiggle right there then connects the oxygen to the R group. So again, triflate is the way we say it. Trifluoromethane sulfonate is the proper term. OTF is the abbreviation, and so this would be, say, ROTF. That would be this molecule right there. Mesylate, methane sulfonate, OMS. Again, it would be ROMS. Tosylate, ROTS. para-toluene sulfonates. These three are really good leaving groups, relatively speaking, because in all cases they leave as the O minus, which is stabilized significantly by resonance. If I put a minus on this oxygen, it can go to any of those oxygens as well. So it's stabilized by resonance, so it spreads the charge out nicely. It's fairly polarizable, that charge. And in addition, these are all the conjugate bases of a strong acid. This is sulfuric acid. If R is OH, this is sulfuric acid with pKa that's less than -5. It's a strong acid. So these guys are perfectly content to exist as the conjugate base of a strong acid. Again, the details here change depending on the nature of the R group. For sulfuric acid, it's on the order of -5, but we can get to, say, -10 or below with a triflate of the right variety. The strongest of these groups is the triflates. Mesolates and tosolates are roughly equivalent in terms of their leaving group ability. In my experience, mesolate's a little bit stronger leaving group. But again, the point is, broadly speaking, that mostly when you're thinking leaving group, you're actually thinking halogen, iodine, bromide, chloride, or things that act like halogens, which are this group of three: triflate, mesolate, and tosylate. Bigger is better, so iodine's better than, say, chlorine, and charge is bad. Having a water leave as water is something that's acceptable. It's slow, it's not necessarily good, but it's acceptable. Having OH minus leave is something that essentially never happens. A pKa of 16 suggests it's far too strong of a conjugate base to leave on its own. You really need to have the counter ion of a strong acid. You really need to have the conjugate base of strong acid. You need this to be a pKa of -2 or so in order to contemplate it leaving. Because of that, in the Pelkey handout, you'll notice that fluoride is deemed to not leave ever. And that's because its pKa is about 3 for HF. It does not want to leave the F minus behind. So, leaving group ability is really about stabilizing charge. Bigger and more polarizable is better. Resonance is good. Leaving as a minus charge that cannot be stabilized by resonance and is relatively small, those are bad things.
I want to finish the consideration of leaving group ability by thinking about the resonance of the structures involved. And so here you have different examples of things that we've contemplated as potential leaving groups. We have hydroxide itself, the conjugate base of water with a pKa of 16. We have methoxide, the conjugate base of methanol, again with a pKa of 16. Then we have the conjugate base of acetic acid with a pKa of 5, and the conjugate base, hydrogen sulfate, of a very strong acid, sulfuric acid. Hydroxide and methoxide are so bad as leaving groups that you essentially consider them never to leave unless the reaction involved is using strong base. So in the case of substitution reactions, these essentially cannot be considered to be leaving groups. Heat up the reaction enough, use strong enough base, and maybe we can get them to fall off. Broadly speaking, they're not considered to be leaving groups. This is obviously dramatically better as a leaving group with a much lower pKa. This minus ion is much happier existing this way. But still, generally speaking, we would not consider an acetate ion like this to be a leaving group. By contrast, a sulfate and a sulfonyl of the type that we talked about already, a sulfonate, say a mesolate, a triflate, or a tosylate, those are considered to be good leaving groups. And again, the difference is the pKa is -3, which is to say lower than the pKa for hydronium, -2. Why are these such bad leaving groups? Essentially, it comes down to resonance, and in this case, the lack of resonance. That minus charge is localized on the oxygen in both cases. Therefore, it's stuck there, and there's really no stabilization possible. It is dramatically better, of course. In both of these cases, we have resonance, and that's the 10 to the 11th difference going to acetic acid, and an additional 10 to the 8th going to sulfuric acid. What it comes down to is a number of good, valid resonance structures. So this carboxylic acid has 2 oxygens and can spread the charge around much better. The sulfonyl type groups have 3 oxygens, and each oxygen only has to bear about 1/3 of a minus charge, as opposed to 2 oxygens in the case of the acetate. Here below, we have the groups we were talking about, the actual pKa's for the acids associated with a triflate, a mesolate, and a tosylate. And what you see is that the triflate has a very, very strong acid. It is what we call a superacid, one of the strongest organic acids, whereas these are in the neighborhood of hydronium and not too far away from sulfuric acid, and they're more similar to each other than not. Incidentally, I mentioned that in my experience, mesolate's a little bit better of a leaving group, and that's largely due to its size, not due to the stabilization of the minus. But one question comes to mind, and that is, why is this so much stronger of an acid? And the answer really has to come down to the fluorines. The fluorines there are serving as inductively withdrawing groups. So the fluorines are pulling electron density away from the oxygen. So the oxygens in all three cases nominally have about a third of a minus charge on them. But these fluorides pull electron density inductively through the sigma bond framework. So they pull electron density toward themselves, and that dramatically lowers the pKa of the acid. Again, 3 fluorines makes an enormous difference, and so the pKa goes from about the same as hydronium or maybe sulfuric acid to 10 to the 12th better, one of the strongest acids known. This is, incidentally, why triflate is such a good leaving group. Having a minus on this oxygen is really not a problem at all. Everything in this molecule is set to protect that and distribute that charge away from the oxygens.